Another kind of chemical reaction we would like to look at is called a double displacement. Turns out that there are two kinds of double displacements. The one that we're going to look at in this video is called an acid-base neutralization. So the general theme to a double displacement is that you have a compound made of a cation A and an anion X that reacts with another compound that its cation is B and anion is Y. The hallmark of a double displacement is that the A and B in the respective compounds swap locations. So that would give us products of BX plus AY. It turns out that these are called acid-base neutralizations because the only compounds that can be our first compound are strong acids, and the only kinds of compounds that can be the second one are strong bases. And what is the definition of a strong acid and a strong base? These are compounds that completely dissociate in water. So all strong acids and strong bases are considered aqueous and completely dissociate into their cations and anions in solution. The other part of the neutralization name is the fact that the two products that are created, the product compound with BX is considered a salt, and the product AY is always water. And when you take the pH of these products, they end up being a neutral pH, which is a pH typically 7. All right, so what I want to do is go ahead and show you an example of an acid-base neutralization reaction, but I also want to give you some specific compounds that are considered strong acids and bases. So any of the types of examples of reactions I'm going to give you, we are going to be using these specific strong acids and these specific strong bases that I'm going to show you now. So it turns out that the strong acids, there are 7 strong acids. Sodium bromide, sodium iodide, sodium chloride, even all the way to sulfuric acid here at the end, are all considered strong acids. And there are 8 strong bases, from sodium hydroxide all the way to strontium hydroxide. So commit these to memory, write them down as something that you can look at so that you can have all of the 7 strong acids and the 8 strong bases. So let's look at an example of an acid-base neutralization reaction. So here you have hydrogen bromide, or hydrobromic acid, sorry. And hydrobromic acid is one of our strong acids. And then you have potassium hydroxide is one of our strong bases. So if you look at the A and the B in these first reactants, they will swap locations. And what that creates is potassium bromide as your salt, and you'll have HOH or H2O as your water. Now, it's very easy to identify an acid-base neutralization reaction, which I want you to be able to do, but I also want you to be able to determine the driving force for this reaction. And to be able to define the driving force of the reaction, we need to be able to determine the net ionic reaction. So that's where we're going to go. We want to look for the net ionic or equation for our acid-base neutralization. So in this case, we're going to have to make sure that we have phase labels for each of our substances. And we know that all strong acids and strong bases are all aqueous. They completely dissociate in water. So we can put AQ here and AQ here. Water will always be in liquid form, so we'll put an L. And all of the salts formed from any strong acid and any strong base are also considered AQ. So the acid-base neutralization, determining their phase, is actually incredibly easy. So let's start by writing our complete ionic equation. And we're going to take HBr and separate it into its respective cation and anion. And so we'll have H plus and Br minus, and we will bracket those. Now keep in mind, before you start doing this, make sure that your original molecular equation is balanced. This was balanced to begin with, and so we're just going to go ahead. So the next compound, KOH, will separate into K plus OH minus and bracket. And then we have potassium bromide, K plus Br minus. And then we'll have our water. We'll write that exactly as is because it is in liquid phase. And now we're going to take our spectator ions out, which bromine, or Br minus, happens to be one. Potassium, K plus, is another. And then we're left with everything that is not considered a spectator ion. And so for our net ionic equation, we are left with H plus OH minus yields H2O. So that is our net ionic equation. The driving force for this is the formation of liquid water. So let's try this one more time. Let's do another example. Here's an example of you have a strong acid and a strong base, and we're going to produce a salt in water. And what we want to do here is we can classify this as an acid-base neutralization because we know HClO4 is a strong acid and CaNOH2 is a strong base. So we know that that's going to be an acid-base neutralization reaction, but I want you to take this a little further and determine the driving force for this reaction. So we're ultimately going to figure out the net ionic equation. And so we need to assign whether something is aqueous or liquid or whatever. So we know all strong acids are aqueous, all strong bases are aqueous, all salts of acid-base neutralizations are aqueous, and the water in the end is a liquid. And so let's take our HClO4 and let's separate that into cation and anion. The cation is going to be H plus, and the anion is going to be ClO4 minus. And keep in mind you have that subscript or coefficient 2, so you do have to put that with each one of your anions and cations. So we'll have 2 and 2, and then you can bracket. And then we have our calcium hydroxide. Calcium is a 2 plus, and your hydroxides are all -1. And it turns out because you have 2 of them with the parentheses around the polyatomic ion, we do need to put that as a 2 in front of the hydroxide. And we'll bracket. And we're going to do the same thing for our salts. We have calcium 2 plus ClO4 minus, and we happen to have 2 of those, so we'll put a 2 and then bracket. And then we'll leave our 2 waters alone as is. Now let's find our spectator ions. Calcium is a spectator ion, and ClO4 is a spectator ion, and so we can cut those out and we write what's left over. And so that means our net ionic equation is 2 hydrogens, or 2 H pluses, plus 2 OH minuses yields 2 waters. And we can even further simplify that by reducing the coefficients and dividing each one by 2 to give us H plus OH minus yields H2O. Do you guys notice anything about the answer to this example compared to the one previous? Do you notice how it's the same answer? Well, that's by design. It turns out no matter what strong acid or what strong base you use to do a acid-base neutralization reaction, you will always get the answer of H plus OH minus equals H2O as your driving force for a reaction. And so that will be your net ionic equation every time. So at this point, what I would like for you guys to do is let's take this a little further. Since you know the scheme of AX plus BY yields BX plus AY, I want you to be able to not only take and identify an acid-base neutralization reaction, I want you to predict the products and then determine the net ionic equation. So what you do here is let's identify the A and the B, and let's swap them with their corresponding anion. So what we're going to do is we're going to start out and make BX, so that means we're going to put lithium with the polyatomic ion nitrate. So lithium is a +1 cation and nitrate is a -1. So when we build this compound, we will only need one lithium and one nitrate ion to form that neutral compound. And then for the AY, we will take our A and put that with OH. So this is H plus and OH minus. And you may think that you can write that this way, H plus OH minus. But we don't write this in that form. You guys know that we write it as H2O. All right, so these are our predicted products. Now what we want to do is make sure that everything is balanced, and it looks like everything in this reaction is balanced the way that it is. We need no coefficients, so now we can actually go through and figure out our net ionic equation. Again, remember strong acids are aqueous, strong bases are aqueous, salts of both strong acids and bases are aqueous, and our water is a liquid. So for our complete ionic equation, we start with H plus and NO3 minus and bracket those. For our strong base, lithium plus OH minus, and bracket our lithium nitrate gives us Li plus NO3 minus, and then we leave our water. Our spectator ions are going to be Li plus and NO3 minus, and we can take those out. And as expected, because remember this is an acid-base neutralization reaction, you get H plus OH minus yields H2O as your net ionic equation. All right, so at this point what I would like for you guys to do, here are some more examples of which you can predict the products, you can determine the net ionic equations for these particular acid-base neutralization reactions. What I'm going to do is I'm going to pause and I'm going to work out the answers for you, and then I'm going to rejoin the video and you can see the answers. So before you see the answers, why don't you pause the video, try to do these on your own, and then you can press play and then see the answers in just a few seconds. So here are the answers for your predicted products and the equations balanced. And as you know, all of these should go through the, going through the complete to the net ionic equation should give you a net ionic equation of H plus OH minus yields H2O. All right, I'll see you in your next video.